So one of the things we could do is like talk about why why something like x squared 2x squared plus 5x minus 3 less than 0 is not going to so nicely break into two pieces. So this is going to be some basic pre-calc stuff, but it is helpful because there's all sorts of little stuff that people keep skipping when we're teaching stuff because, you know, we don't have time, quite frankly. Anyway, for this, I use AC method on this. If you've never seen the AC method, I would not be surprised because I didn't learn it until I started teaching. I was shocked. So anyway, you've got 2 and 3 are going to be potential factors for 6, and 1 and 6 are going to be the others. Why does this work? Well, we're trying to factor this thing into something that looks like ax plus b times cx plus d. And if we multiply all this stuff out, this becomes a times c x squared plus ad plus bcx plus bd. And what we've done here is we always say like, oh, we're going to multiply our a value up front and our c value at the end. All right, why? I should not use a, b, c, and d. Yeah, that's an amateur mistake. I should have remembered that. Oops. That's awful. Okay. Alright, don't use other constants that you already have in use somewhere else. So we have a, b, and c here for the quadratic, and we want to factor this into mx plus n times px plus q. Alright, which multiplies out? mp times x squared plus, this is mq plus np times x plus nq at the end. Okay. Now what I did was I took a times c, which was the first times the last. In this case, the first is mp and the last is nq. And what we're saying is that we want to split the factors that we just got, a times c or mp times nq, into two numbers whose sum will be the middle term. So we want to split this into mq and np, which is possible because, again, this is multiplication. And by the commutative law of multiplication, you can do multiplication in any order you want. So we want this to be mq times np, and then we want to be able to add them together and get the middle term, so 5 in this case. Now, one of the reasons that I use this particular example is because 5 can be received in two different ways depending on what the signs are for your values, for your factors. It's one of my favorites just because students always jump to 2 and 3, because 2 plus 3 is 5. And half the time they're right, half the time they're wrong. So in this particular case, what I like to do is say, all right, here you're adding up two numbers, mq plus mp, and we're going to get a positive 5. Now, in order to get a positive number from summing stuff up, it has to be true that the larger number is going to carry its sign through to the end. All right, if they're both positive, then the result will be positive. But if they're one positive, one negative, then it gets ambiguous. Well, the bigger one will have some of it some of its number canceled out or added together to be equal to 0 with the entire negative number. Or if the negative number is bigger, then it will have some of its numbers eaten away by the positive value that we had mixed in with it, the smaller positive value. So here this is telling you this is flat out telling you what the sign of the bigger number is going to be. So I go down my list and I make all the bigger numbers positive. Then we go over here and you say this is what happens when you get the product of these two numbers n and q. Since our a value here was already positive, I hope it was already positive. For anybody who's doing the AC method, you want to make a positive. It just makes your life a whole lot easier. Then that means that m times p is at the very least going to be the same sign. So both could be positive or both could be negative. But most of the time we're going to let mp each be positive and just leave it as that. Which means that nq is then going to, in this particular case, tell you whether the signs are going to be the same or the signs are going to be different. If they're the same, then when you multiply them together, you get a positive. If they're different, you multiply them together, you get a negative. So in this particular case, this is telling us that this is going to get us two different signs. Since the top ones, or the higher ones, were all positive, the lower ones must therefore be all negative. Then there's only one that's going to add up to positive 5, and that is negative 1, positive 6. So 2x squared minus 1x plus 6x minus 3 is less than 0. We can then factor each of the sets of terms. So here we factor out an x, we're left with a 2x minus 1 plus 3 times the quantity 2x minus 1. If these are not the same, then you did something wrong. Factor out 2x minus 1, you're left with x plus 3, et voila, you have everything you need for this inequality. Now, the problem that a number of my students this semester said was, oh, you just say that 2x minus 1 is less than 0 and x plus 3 is less than 0. To which I said, oh, you make my head hurt, please stop. No, I don't actually say that. You gotta be nice and stuff, you know. So yeah, you have to be very careful when you do this, because again, looking at this, this is the product of two numbers, 2x minus 1 and x plus 3, which is getting us a solution or a product which is less than 0. Well, if a product is less than 0, then that means that the signs were different. We just did that. Right? We literally just did that up there. So if the signs are different, that means that if 2x minus 1 is less than 0, this means that it must also be true and that x plus 3 is greater than 0. So if this one is negative, then this one must also be positive. Or the other option is that x plus 3 is negative and 2x minus 1 is positive. This is why I tell my students, don't do this. Don't try and factor this by hand. Don't try and come out with inequalities and solve it algebraically. Instead, you can solve it using test values, and it becomes much easier. We'll do the test value one next. So here, am I covering? No, okay. So here, with these two, we see that x must be less than negative 3, and also here, this is plus 1 divided by 2. X must be greater than a positive 1/2. Okay? It says that we must both have that x is less than negative 3, so we're going to be going that way, and also greater than 1/2, so we're going to be going that way. And an AND statement says that we're trying to find the intersection of these things. So where do they overlap? Well, they don't. So this is not possible. This whole solution is out. And then we can work with this one here. So 2x minus 1 is less than 0 is going to be that x is less than 1/2, and also x is greater than -3. Okay, -3, x is greater than -3, it's that way. X is less than 1/2, it is this way. And now we want the intersection, so this is open circles at -3.5 and shade in between. These are acceptable values here. Alright, so that's the AC method, and this is why I don't do algebra beyond this point here. I'm going to recommend that everybody I meet go about this with test values in mind. So what we're going to do here is say that we're actually not going to do that yet. We're going to say that 2x minus 1 times x plus 3 is going to totally be equal to 0 and not 100% totally not just making this up. So what I'm doing here is I'm saying that we're not really this isn't really equal. What we need to do is find the border points between the prospective solution regions. So if this were an equation, then we'd be able to solve this as, just like the people earlier said, 2x minus 1 is equal to 0, or x plus 3 is equal to 0. When you do this, x must be equal to 1/2, or x must be equal to -3. Again, we've already seen these numbers pop up from this side, but we're going to do this again as test values. So the solutions to this are going to be a -3 and a positive 1/2. But the test values are going to be something out here. So I'm going to do -4, I'm going to do 0 in between, and I'm going to do 1 outside on the positive side. Then we can go back to the beginning, or you can go back just here and look at the individual values themselves. So if we plug in -4 to here, we get that -4 plus 3 is -1, and -4 times 2 is -8, minus 1 is -9. So we get two things that are both negative. That means that in the original equation, right, their product, actually let's go to this inequality, factored, their product is going to be positive. A positive number is less than 0? Yeah, I don't think so. So a positive number less than 0 is going to fail, and therefore there are no solutions in this region containing -4. At 0, we can see that we're going to get 0 minus 1 is a negative, times 0 plus 3 is a positive. So negative times a positive is less than 0 because that is negative. Negative less than 0. Cool. So we're going to shade in the region that contains 0, and its border points, -3 and 1/2, are both going to be not allowed, because here this is not less than or equal to, it's just strictly less than. So we go over and we say, well, it can't be equal to, really. So we get everything between -3 and 1/2. And if we plug in a 1, same deal. Plug in 1 here, you get 2 minus 1 is going to be 1, times, this is 1 plus 3 is positive, or a 4. So then you get a positive less than 0. And again, that's not going to work for us. So the solution region here, whether we found it using the strict algebra or find it using test values, you're going to get the same thing. That x is only going to go from -3 to +1/2.